Siin loengus vaatame pneumaatika täituritest ja kuidas nad töötavad.
Pneumatic cylinder is a linear actuator powered by compressed air to supply force on a load. The assembly shown here is the most common type of double-acting pneumatic actuator used in industries. It consists of a piston rod. This rod transfers force of compressed air to the load. Cushioning pistons are assembled with this rod. These pistons prevent any hard shocks at the end of the stroke by enabling the piston to stop slowly and gradually. The piston reciprocates back and forth when there is pressure difference between any of the two sides. A static seal ensures airtight sealing between the piston and rod. Piston guide rings are assembled to prevent metal-to-metal contact of piston and cylinder. Piston seal provides airtight sealing between the cylinder and piston. This whole assembly then goes into a cylindrical bore. This cylinder is generally made up of aluminium or steel. A cylinder cap encloses cylinder chamber in one end and the cylinder head encloses a chamber from the other end. Cushioning buffers and seals are installed on respective ends. Captive adjustable cushioning screws are installed on each end. These screws enable user to adjust the optimum cushioning at the end of the stroke. This whole assembly is held together with tie rods. These rods also provide compressive and tensile strength to the actuator. Air ports are screwed to the ends through which compressed gas flows in and out. A pneumatic valve is connected to these air ports using pneumatic hoses. The valve shown here is a 5-port 4-way valve. The ports A and B are connected to the cylinder. Port P is connected to the compressed air supply unit. Ports R and S are exhaust ports to which the pneumatic mufflers are attached. Now let's understand how a pneumatic cylinder works. The compressed air is supplied through inlet port P of the valve. The valve directs air to a particular direction, which we can observe in the animation. In this case, the air is directed to port A. This high-pressure gas is then transferred to the cap end of cylinder through the pneumatic hose. This creates high pressure in the cap end of cylinder, which therefore pushes the piston towards the head end. This also pushes gas from the head end. This exhaust gas travels through the other hose and reaches the valve. The valve directs this gas towards port S and allows it to escape through a pneumatic muffler. The gas muffler helps to reduce any noise produced during exhaust. The process we just observed is the extension stroke of actuator. During the retraction stroke, the valve directs compressed air to the head end of cylinder. This causes the piston to return and air on the other chamber escapes from the exhaust port R. The theoretical force of actuator is the relative pressure on the piston multiplied by effective area of piston on which pressure is exerted. Here, the relative pressure is pressure of supplied air minus the atmospheric pressure. During extension stroke, compressed air can exert pressure on total cross-sectional area of piston. This gives us the expression of theoretical force as relative pressure multiplied by total area of piston. During retraction, the effective area of piston is reduced because the air cannot exert pressure on the area of rod. This gives us the expression of theoretical force as relative pressure multiplied by partial area of piston. Frictional losses on the interface of different surfaces also needs to be considered while designing pneumatic cylinder. The diameter of rod and length of stroke is also a determining factor for capacity of actuator.
Lineaarliikumisega täitureid või pneumosilindrit kasutatakse lineaarliikumise saamiseks mehaanistes süsteemides. On olemas ühepoolse toimega silindrid. Ühepoolse toimega silindri puhul juhitakse suur õhk ainult ühelt poolt sisse. Sellise silindrina kasutada juhtuval, kus on tarvis sooritada tööliikumine ainult ühes suunas. Kolvi tagasiliikumine toimub silindrisse sisseehitatud vedru mõjul. Tagastusvedru jõud on arvestatud selline, et tagada piisav kiire kolvi tagasiliikumine. Ühepoolse toimega silindri on kolvi liikumisulatus piiratud. Üldjuhul ei ole see suurem kui 100 mm. Seda tüüpi silindrid kasutatakse lukustamiseks, kinnitamiseks, kokkusurumiseks, tõukamiseks, tõstmiseks ja detailide etteandmiseks. kasutusel on kahte tüüpi ühepoolse toimega silindreid. Paremapoolsel pildil on kujutatud silindri tingmärke, kus töö liikumine toimub vedru mõjul. Kolbi tagasiviimine lähteasendisse toimub aga suruõhu mõjul. Sellist silindrit kasutatakse siis, kui on olemas suruõhk kadumise oht, näiteks autode või rongide pidurisüsteemides. Ja vasakpoolsel pildil on näidatud siis vastupidine toime. Membraansilindrites asendab kolvi kas kummi või plastikmembraan. Kolvi varras on kinnitatud membraani keskele. Sellises silindrites ei teki liikuvat tihendust. Tekib ainult membraani deformatsioonist tekkiv elastsusjõud. Pildil on siis mõlemapoolse amortisaatoriga varustatud pneumosilinder. Kolvi liikumine silindris toimub suruõhu mõlemas suunas, nii miinuses kui pluss suunas. Kahepoolse toimega silindril on kasutusel juhul, kui on valik sooritada kasuliku töö mõlemas suunas. Kolvi liikumisulatus on kahe toimes silindri puhul praktiliselt piiramatu, kui see peab olema selline, et silinder säilitas jäikuse. Kui silindrit kasutatakse suurte masside liigutamiseks, siis kasutatakse löökide ja purunemise vältimiseks silindrile sisse ehitatud amortisaatoreid. Kui kolb on jõudnud piirasendisse, sulgeb amortisaator kolbi välja õhule otsevoolu, nii õng pääseb läbi trosseri. Seetõttu liigub kolbi piirasendisse aeglustusega. Enamikel juhtudel on aeglustav reguleerituv. Silindri teise suunalise liikumise pääseb õhk kolbi taas otse läbi mööda võluklappi. Siin pildil on siis mitmed tingmärgid. On olemas ka erikonstruktsiooniga kahepoolsed silindrid, näiteks läbiva kolvivarrega pneumosilinder. Seda tüüpi silindrid läbib kolvivarras ja väljub mõlemast silindri otsast. Siin on kolvivarre liikumine täpsem. Samuti taluvad need silindrid ka suuremaid kolvivarrega risti mõjutavad koormuseid. Tandemsilinder koosneb kahest järjestikus paigutatud omavahel mehaaniliselt seotud silindrist. Sellise konstruktsiooni puhul kolbide poolt arendatud jõud summeeritakse. Seda tüüpi silindrit kasutatakse rohtades, kus vajatakse suuri jõude, kuid kus seadme konstruktsioon ei võimalda kasutada suurema läbimõõduga silindreid. Siin pildil näeme mitme positsiooni silindreid. Need koosnevad vahel seotud kahest tavaliselt pneumosilindrist. Kuna silindrite juhtimine toimub kummalgi silindri eraldi, võimaldab selline konstruktsioon positsioneerida tööorganid 4 erinevas asendis, mis on ära määratud kolbide liikumisulatuses. On olemas ka lööksilinder. Normaalsilindri puhul on arendav jõud liikumisenergia on mõni kasutusvaldkonnas ebapiisav. Sellisteks juhtudeks sobib lööksilinder, mis võimaldab saavutada suurt liikumisenergiat. Lööksilindri kolvi liikumiskiirus ulatab 7–10 meetrit sekundis. Seda tüüpi silindrit kasutatakse tantsimisel, neetimisel ja nii edasi. On olemas ka trossilinder ja selle põhimõtteliselt kahepoolne toimega silinder, mille kolvi külge on mõlemalt poolt ühe pöörarullikutega kinnitatud tross, mis jäigalt seotud väljaspool silindrit paikneva liuguriga.
Deposit these workpieces in a controlled manner. Even rotational movement can be executed. It is up to you to consider and choose the appropriate type and size cylinders. Next is an overview of the most common cylinder types, which we will review and discuss in this video.
The function of cylinders with a piston rod is very simple. A tube, closed on both ends with a cap and heat, has a drive piston. The double-acting cylinder, as shown here, has 2 inlet ports. The movement of any cylinder is triggered by compressed air. High pressure on one side drives the piston to the other side. Here the piston force can be built up in both sides. That's why this type of cylinder is called a double-acting cylinder. This piston force can be calculated by the law of Pascal. If you have pressure on both sides, the effective piston force is the difference of the forces on the piston and rod side. Normally, double-acting cylinders are actuated by a directional spool valve with 5 ports. Our way valve shown here has 2 switching positions, so you call it 5x2 valve. The way valve directs the compressed air on port 1 to the air ports of the cylinder. Exhaust air from the cylinder is directed to exhaust ports 3 and 5 with these pneumatic mufflers attached. When the piston hits the head or end cap, it creates a hard shock. Besides the stress on the cylinder components, it is noisy and transmits vibration to the machine. Cushioning is a possibility to decelerate the piston at the vicinity of the caps to prevent these hard shocks. By trapping a certain volume of air in the end position, a braking effect can be generated. With an adjustment screw, you can get the ideal cushioning. Too much cushioning results in slow strokes, and too little cushioning increases the end-of-stroke shock. Especially for sequence controls, you need to detect the end positions of the cylinder. Here, reed sensors are mainly used. To be able to use these sensors, the piston is equipped with a magnet. So when the piston approaches the reed, you get a signal to the control. In summary, double-acting cylinders can have long strokes, up to several meters, with a constant output force through a full stroke. They give the user full control as they can be stopped in any position. But in case of a power loss or pressure failure, you don't have a defined cylinder position. In addition, the air consumption is relatively high as you need compressed air to retract these cylinders. In single-acting cylinders, only one chamber is inflated with compressed air. That's why a piston force is built up in only one direction. The inbuilt spring has the only function to retract the piston automatically when no pressured air is switched to the cylinder. Depending on how this spring acts within the piston, you can distinguish between two different types of single-acting cylinders with different base positions. Base position minus is the common one. As the single-acting cylinder has only one inlet port for the compressed air, you would use a 3x2 directional spool valve. In our example here, we use a spring-loaded directional valve. Due to the inbuilt spring, the piston returns to its base position in case of a power loss. Besides this, the air consumption is about the half of a double-acting cylinder of the same size. However, this inbuilt spring leads also to an inconsistent output force through full stroke and less efficiency due to the opposing spring force. In addition, the stroke is limited by the spring length ability. In general, single-acting cylinders offer a relatively short stroke compared to the double-acting cylinders. Whereas a traditional pneumatic cylinder uses a rod to push or pull the load from the piston, a rodless cylinder moves the load alongside its piston. As a result, you get the same stroke length but in less space, same force in both directions, and no rod buckling with high loads and long strokes. Different types of rodless cylinders can be distinguished by the way the piston is connected to the carrier. One principle is the magnetic coupling. Here, the piston and slide are connected together by using permanent magnets. One magnet integrated within the slide, the other one within the piston. In this design, the piston can move in a completely enclosed thin steel pipe. You get a leak-free cylinder with less wear compared to the other types of rodless cylinders and no ingress of contaminants. However, the magnetic coupling is also a force limiter. If the load is too high, you have to worry about decoupling. If you want a rodless cylinder with a high cylinder force, you would choose a slotted rodless cylinder. Here, the piston is mechanically coupled to the carrier. An inner and outer band keeps the air within the barrel of the cylinder. But how so? As the piston drives, the two-band sealing strips open in front and then close behind, regardless of the direction of travel. The seals of the piston inside the cylinder barrel press the inner band tightly against the barrel of the cylinder, preventing air leakage. The outer band is pressed tightly against the outside of the slot of the cylinder barrel with the so-called shoes of the carriage. And it's working! Here you see a band cylinder totally dismounted and fit together again. Inner and outer bands may wear over time as they stretch. As a result, you can get air leaks and loss of air pressure. It is up to the maintenance to replace these bands, especially for expensive cylinders. The last type of rodless cylinder is the so-called cable cylinder. Here, a cable is connected to the piston and drives the carriage through a pulley on each end. This is a very simple design. That's why cable cylinders are relatively inexpensive. But the weak point is the cable itself. Cable wear causes inconsistent positioning, and leaks can occur from stretched cables. You need extra distance? Then take a telescoping cylinder. Also called a multi-stage cylinder, this type of cylinder consists of a series of tubular rods called sleeves. These sleeves sequentially decrease in diameter and are nested inside of each other. Once pressure is switched to the cylinder, the main sleeve first extends. Once this sleeve is fully extended, the next smaller one begins to extend. Telescoping cylinders provide an exceptional long output stroke from a very compact retracted length. They can be designed as single-acting or double-acting cylinders. Pneumatic rotary cylinder converts compressed air pressure into a rotary motion. One of the most widely used designs is the rack and pinion rotary actuator. A long piston with gear rack teeth meshes with a pinion mounted to an output shaft. The output shaft of this double-acting cylinder rotates counterclockwise by pressurizing the right-hand chamber. Compressed air on the left-hand chamber produces clockwise rotation. Rack and pinion rotary cylinders offer a wide range of torque and rotation. They are mechanically stable and provide radial load support. Vane cylinders have a cylindrical chamber in which a vane is mounted to a central shaft. Air pressure on one side forces the vane to rotate until the end of the stroke is reached. You get vane actuators in two designs. The single vane design has a relatively large rotary motion, up to 280 degrees typically. The double vane type offers a less rotational range, which is limited by half but produces twice the torque. This type of rotary cylinder uses external methods to limit the rotation or to cushion the load. The end position of our cylinder here is detected mechanically. Compared to the rack and pinion cylinder, vane actuators are compact in size and less expensive, but the cycle life is limited by the wear of the vane seals. Also, friction caused by the vane seals and leakage over these vanes result in less efficiency.
Besides a short reaction time, the clean working medium air can even be used in hazardous or explosive areas. Pneumatic cylinders and pneumatic motors cannot overheat due to overload, and maintenance is very simple in most cases. This is why pneumatic cylinders will always have their place aside electric actuators. For more information about pneumatics, please visit our webpage. Subscribe to our channel and never miss a new video.